Okay, so for lesson 11 and actually lesson 10 together, the in-class work, I will just keep working on the problems from that worksheet. So problem 2. We are playing a game by drawing a card from a standard deck and replacing it. The card is a face card. In this case, you win $30, and if it's not, you pay $2. There are 12 face cards in a deck of 52 cards should you play the game. Okay, so now first of all, let's understand the question. So obviously there is a gain, right? And if we think about it, the time, the probability that we win, right? So the probability of winning, it's when x equals to the win, then that would be what, 12 out of 52. Okay, and the probability of losing is going to be 40, right, out of 52. So in 40 cases, you lose $2 and win. All right, so now we need to make sure that we know what our x is. Now, when you have a question, should you play the game? What do you think you will be interested in? You probably would be interested about the amount of money you either win or lose. So let x represent the amount of money. Well, of course, we need to choose win or lose. Let's do win. The amount of money you win. Okay, then let's construct a probability distribution table. So I'll have x here and p of x. So now I'm gonna use more probability distribution language, and instead of w and l, I'm just gonna put x. Okay, so x can be equal to 30 because that's a win, or we can lose $2. Now let's think about how we can express it in terms of x, which is a winning and amount of money we win. Well, we'll do it in a very simple way. We will put a -2, right? So we have kind of a positive win when we actually win money and a negative win when we actually lose money. Okay, now probabilities. So we already calculated that the probability of getting $30 would be 12 out of 52. And 40 out of 52 will probability of losing. Okay, so now next step is to actually look for the answer. Should we play the game? So for this, what we'll do is we will find the expected value. As you remember, the expected value is the mean of the probability distribution that is equal to sigma x p of x. So let's do it. So I will find x times p of x here. So that would be 30 times 12 over 52. And this will be negative 2 times 40 over 52. For convenience, I will move for addition here. 30 times 12 over 52 minus 2 times 40 over 52. So I will simplify a little. Here we'll have 15 times 12 over 26. minus, that is here, 240 over 26, I'm sorry. 50, not 52, 26 now. I can even do a little more, right? Divide by another 2. So I will have 15 times 6 over 13 minus 20 over 13. Okay, now 15 times 6 is 90. 90 minus 20 is 70, so it's 70 over 13. Okay, so this will be 5 point something, but the main thing that it is a positive number, right? So you can calculate the exact number of dollars and cents, you win. So on the long run, if you keep playing this game, you should be in positive win, right? Which means that the answer is yes, you should play the game. Okay, so let's write it down as a yes. And on the long run means that you do play many times. Okay, now let's take a look at the next problem. So here I have a situation. So a nurse commented that when a patient calls the medical advice line claiming to have the flu, the chance that he or she really has a flu is only about 4%. Of the next 25 patients calling in claiming to have the flu, we're interested in how many actually have the flu. And we need to define the random variable x. Okay, so according to the problem, the random variable x will be equal the number of patients that truly have the flu. Okay, so now let's list all possible values of x. So 25 patients called, so we may have that situation when none of them really has a flu, or 1, or 2, or all the way to 25. Okay. Now let's take a look at part B. That says state the distribution of x. Okay, so let's see. First, I'm looking at the 25 patients, and this is my n, so it's fixed. Secondly, this is a yes or no situation, right? The patient either truly has a flu or the patient doesn't truly have a flu. 3, does it have the fixed probability? So we know that the observation of the nurse said that the probability in general population, for the general population, that the one person that calls really has a flu is 4%. Okay, and we consider each call to be independent. So, since all 4 conditions hold, we can say that x is distributed binomially. The parameters for the distribution are NP, so it's 25 and 0.04. Alright, now let's find the probability that at least 4 of the 25 patients actually have the flu. Okay, so I need to do it in a way that at least 4. So this is a probability of x greater than or equal than 4. So this is actually, this question actually includes a lot of probabilities to find. So I actually need to find the probability that x equals 4, then or it can be 5, x equals 5, and all the way up to x equals to 25, right? Because they all would satisfy the condition of being at least 4. And of course, I'm not going to do it by hand. I'm going to use a calculator real quick. Okay, so I'm using StatTrak binomial calculator. And in this calculator, I need to enter the probability of success in a single trial, which is going to be, in my case, 0.04. Number of trials is my n, which is 25, and number of successes is equal to 4. And I'll click calculate, and now I have all the numbers for different, for the variety of probabilities, right? X equals to 4, less than 4, less than or equal to. I'm interested in greater than or equal to. So the probability that I see in this calculator is 0.01. I'll do 4 digits, 0165. Okay, next question. On average, for every 25 patients calling in, how many would you expect to have a flu? So this is the expected value, and the expected value is a mean. And mean is equal to n times p. So n is equal to 25 multiplied by 0.04, and this is 1. So out of 25 patients called, I would really expect only 1 to have a flu. And the standard deviation, sigma, is equal to npq, which is a square root of 25 times 0.04 times q. Q is 0.96. And now it's just time to calculate. So that is 1 times 0.96. So actually all we need to do is to take a square root of 0.96. And that is approximately 0.98. 2 digits is enough. Okay, so this is a standard binomial distribution problem. Please make sure that when you prepare for the exam, then you write down not just how the x distributed by y, but why it is distributed this way. So this is a justification of why it really works. And please let me know if you have any questions.